Okay, now that we understand air masses and fronts, we can discuss middle latitude cyclones, or mid-latitude cyclones for short. Middle latitude cyclones are areas of low pressure, remember a cyclone is an area of low pressure, that form in the mid-latitudes. They are also sometimes called extratropical cyclones because they form outside of the tropics, okay, in the mid-latitudes. Usually, they are composed of three air masses, okay, three different air masses with different temperature and humidity properties. In the wintertime, middle latitude cyclones traveling along the west coast have a maritime polar air mass to the northwest, continental polar air mass to the northeast, and a maritime tropical air mass to the south. While those mid-latitude cyclones that move over the east coast in wintertime have a continental polar or even continental Arctic air mass to the northwest region, a maritime polar air mass to the northeast region, and a maritime tropical air mass to the south. Now, the reason that mid-latitude cyclones over the west coast in wintertime have maritime polar air to the northwest is because that's behind the cold front, and remember that weather in the mid-latitudes moves from west to east. So the mid-latitude cyclones moving over the west coast are generally from over the Pacific Ocean, okay? And remember that water cools down and warms up faster than or slower than land. So water has a moderating effect on how cold an air mass is in the wintertime. While the mid-latitude cyclones moving over the east coast are from the interior continental US, okay, and so they're generally colder. The northwest region is colder. Polar front theory is a model used to describe the life cycle of a mid-latitude cyclone. Back in the early 1900s, a group of meteorologists developed a model that helps explain the life cycle of a middle latitude cyclone. They worked largely from surface observations. They were a group of scientists from Norway, including Wilhelm Bjerknes, his son Jacob, Halvor Solberg, and Tor Bergeron. Remember Bergeron, you'll recognize his name from the Bergeron ice crystal process, okay? They published their Norwegian cyclone model shortly after World War I. It was widely acclaimed and became known as the polar front theory of a developing wave cyclone, or polar front theory. What these meteorologists gave to the world was a working model of how a mid-latitude cyclone progresses through the stages of birth, growth, and decay. And an important part of the model involved the development of a mid-latitude cyclone along the polar front. Okay, the polar front, we'll discuss that. We talked about that during atmospheric circulations. As new information became available, the original work was modified so that today it serves as a convenient way to describe the structure and weather associated with a migratory middle latitude cyclone. So it's only a model. There are simplifications to it, and it turns out that few middle latitude cyclones exactly follow the polar front theory, but it is useful to understand how they form, how they intensify, and how they decay. Okay, so let's talk about polar front theory. There are 6 stages of theory, beginning with the stationary front stage. Remember, the polar front is a front that divides polar air, colder polar air to the north, and warmer subtropical air to the south. And you'll remember that there's a polar high, the area of high pressure over the polar region, and a subtropical high, an area of high pressure over the subtropics, okay? And so there are contrasting wind directions on either side of the polar front, okay? To the north of it, the winds blow from the east, the polar easterlies, and to the south of it, winds blow from the west, okay? The westerlies flow in the mid-latitudes. Well, this contrasting wind direction can set up a cyclonic circulation, okay? You can conceptualize the cyclonic rotation that develops if you have a pencil or pen between your hands and you move your one hand one way and your other hand the other way, right? The pen will turn, okay? So under the right conditions, a wave forms along the front and an area of low pressure develops, as shown in B. And the cold front and the warm front meet at the area of low pressure that's formed along the front, okay? And you have colder air behind the cold front, warmer air ahead of it behind the warm front, okay? The wave that forms is known as a frontal wave. Watching the formation of a frontal wave on a weather map is like watching a water wave from its side as it approaches a beach. It first builds, then breaks, and then dissipates. Okay. As the cold air displaces the warm air upward along the cold front, and as warm air rises ahead of the warm front, a narrow band of precipitation forms, shown by the shaded green area. Steered by the winds aloft, that is the winds in the upper levels, the system usually moves east or northeast, and it gradually becomes a fully developed open wave in 12 to 24 hours, shown by part C of the figure. The central pressure of the wave cyclone is now much lower. Several isobars encircle the low. Okay, notice more isobars, and that indicates stronger winds, right? The winds swirl counterclockwise and inward toward the center of the low. Okay, precipitation forms in a wide band ahead of a warm front and a narrow band of the cold front. The region of warm air between the cold front and warm front is known as the warm sector. And here the weather tends to be partly cloudy, although some scattered showers and even thunderstorms can develop if the air is unstable enough. Where does energy for the storm come from? Several sources. As the air masses try to attain equilibrium, warm air rises and cold air sinks, and this transforms potential energy into kinetic energy, the energy of motion. Condensation supplies energy to the storm in the form of latent heat release. And as the surface air converges toward the center of the low, wind speeds can increase, producing an increase in kinetic energy. Okay? As the low moves eastward, central pressure continues to decrease. Winds increase in speed. And the cold front, which moves faster than the warm front, begins to close in on it. Okay? And that causes the warm sector of the storm between the cold front and the warm front to shrink in area. At stage D here, or part D, the fourth stage of the polar front theory, the cyclone is most intense. Okay, and that's when the cold front initially catches up to the warm front. Okay, clouds and precipitation cover a large area. Now, as the cold front continues, more of the cold front reaches the warm front. Okay, the cold front first catches up to the warm front at the northern end of both, and then as time goes on, more of the cold front has caught up to the warm front, so the occlusion covers a greater distance, and so the warm sector of the storm becomes smaller. Well, without the supply of energy provided by the rising warm moist air, the old storm system dies out and gradually dissipates. Okay, there's just not enough energy. The storm's losing energy. Okay, and so eventually the area of low pressure can cut off or break up from the front, and so at F here on the figure, you have what's called a cutoff cyclone. Okay, the entire life cycle of a wave cyclone can last from anywhere from a few days to over a week. So summarizing the polar front theory, During the stationary front stage, there are parallel winds on either side of the polar front, but they blow in opposite directions. And that sets up a circulation. A frontal wave develops, low pressure forms. And the low pressure at the center of the cyclone becomes stronger. Okay, pressure drops and winds increase, and the cyclone becomes an open wave. At the mature stage of the cyclone there is the initial occlusion. The cold front has caught up to the warm front. The northern end has. And as the occlusion covers a greater distance, okay, as the occlusion becomes advanced, cold air now lies on both sides of that occluded front. The system dissipates. And eventually, the low becomes cut off from the fronts, and then that's basically the end of the cyclone. Okay. Now, remember, this polar front theory is a model. Okay, it's a simplified version of the stages that mid-latitude cyclones go through. Okay. Nevertheless, it does serve as a good foundation for understanding the structure of cyclonic storms. Where do cyclones actually form? Okay, well, they can form along the polar front, okay, like the theory says. Now, any development or intensification of a mid-latitude cyclone is called cyclogenesis. Cyclogenesis refers to the development or intensification of a mid-latitude cyclone. And several regions of North America show prosperity for cyclogenesis, including the eastern slopes of the Rocky Mountains, the Gulf of Alaska, the Gulf of Mexico, the Atlantic Ocean east of the Carolinas, and even western Canada. Okay. Here's a figure from the book. It's really made of two figures showing in the upper part typical paths of winter mid-latitude cyclones along with their formation regions. And on the bottom, typical paths of winter anticyclones. Okay. Now the lows, the cyclones are named after the region where they form. Okay. So you'll notice the Gulf of Alaska low forms over the Gulf of Alaska, and it slides east or east-southeast. Okay. And this is the low that can bring rain to Northern California during wintertime. Okay. The Alberta Clipper forms over Alberta, and it slides southeast or east-southeast into the Central Plains and the Great Lakes region. Eventually, it can reach the northeast. Okay, lows often form on the eastern slopes of the Rockies over Colorado and then move northeast. Okay, lows can form over the Gulf of Mexico and then move into the southeast or over Florida off the coast. And it's also common for lows to form off the coast of Cape Hatteras, North Carolina, sometimes from a stationary front present over the region. And then these lows can actually move northeast off the northeast coast, and they can develop into what are called nor'easters or nor'easters for short. And those are those really strong lows, those storms that bring high winds, heavy rain or snow, okay, even rising of the ocean and flooding, okay, to the northeast coast, okay. Now, high pressure systems often form over western or central Canada and then move southeastward, okay, or eventually eastward, okay. Notice that the lows generally move east or northeast, okay. The Gulf of Alaska low and the Alberta Clipper can start to slowly move east-southeast, but generally east or northeast is the direction these lows move, while the highs generally move southeastward, okay, and then eastward. Developing surface mid-latitude cyclones are called dynamic lows, okay. So the mid-latitude cyclones that form at the surface and develop are called dynamic lows. Now, in order to intensify, there needs to be divergence aloft. Divergence is the spreading out of air, okay? So air converges at the surface of a low, okay? In the northern hemisphere, winds blow counterclockwise and inward to the low. But air needs to spread apart, diverge in the upper levels in order for the low to become stronger, right? So in order for a low to become stronger, its central pressure has to drop, okay? Its central pressure has to drop, and then the wind speeds will increase, right? It will become stronger. But for that to happen, there needs to be a net removal of air from the column of the low, okay? Because in order for pressure to drop, there has to be removal of air, right? Less air. And so that there has to be more divergence aloft in the upper levels above the low at the surface than the convergence of air, the air coming into the low at the surface. We'll look at this on a figure. And surface mid-latitude anticyclones that develop are called dynamic highs. Now, for a surface anticyclone, winds blow clockwise and outward in the northern hemisphere. So the winds diverge at the surface, but there needs to be convergence aloft to intensify. For the high pressure to become greater, for the pressure of an anticyclone to increase and henceforth to intensify, there needs to be a net addition of air to the column above the high, so there needs to be more convergence aloft than divergence at the surface associated with the high. So where does divergence aloft happen? To the right side or east of the upper level troughs. Well, convergence aloft happens on the left side or the western part of the upper level troughs. And sometimes mid-latitude cyclones can develop when a stationary front is located below an area of divergence aloft. There's a figure from the book showing the necessary three-dimensional basically picture for lows to intensify and highs to intensify in the northern hemisphere. That is, surface lows and surface highs to intensify. So for the low, there are counterclockwise and winds blowing inward to the low, okay, and rising air above the low, right? Area of low pressure is associated with rising air. But aloft, winds are spreading out, apart. See this div text here? It means divergence, okay? Air has to spread apart aloft. There has to be a net removal of air from the column. And this happens on the eastern or right side of upper level troughs. Remember that the winds blow parallel to the contour lines in the upper levels. Can you see how the air is spreading apart here? Okay, shown by these small spheres. They're spreading apart. Whereas on the western side or left side of the upper level trough, the winds are coming together. These spheres are coming together. The air is converging. Okay. And above the high, there needs to be more convergence aloft than divergence at the surface. In the northern hemisphere, winds blow counterclockwise and outward from the high. Of course, air sinks over the high, right? So, to sum up about the upper level conditions that need to be present for a surface low to develop or intensify. The upper level low, okay, the upper level trough or low has to be to the west or left of the surface low. And if that's the case, there will be divergence aloft, okay, divergence above the surface low, and it can intensify. Okay, that's it for lecture 10.